So today I'll be talking about performance matters. This is joint work with my former graduate student, Charlie Kurtzinger, who's now professor at Grinnell College. So I'm going to start with a little story. It's a short time ago in a valley far, far away. Not this valley, which is really far away, but this valley, which for some of us is quite close and some still far. And in this valley, we have our hero, Luke. So Luke, being in Silicon Valley and not on Tatooine, has an idea for an app. That's how he's going to resist, I guess. So his idea for an app is super compelling. It involves cats, so it's guaranteed to be a success. And the way that the app is going to work is that Luke is going to have this application that lets you take pictures of cats, and then it will go search for similar pictures of cats. So you'll get just as many cat memes as you could possibly want. Just take a picture of a cat and you get cat memes. And he has a great idea for this killer app. He calls it Ogle. Suspiciously sounds like another successful company, which is a good sign. Luke is convinced it's going to totally disrupt image search. Unfortunately, Luke has not heard of Google image search, but that's okay. Nobody tell him. All right. So Luke goes out and he sets out to create his prototype of Ogle. And to get a little deeper into the software architecture of how Ogle is going to work, the way it works, like I said, you take a picture and then it's going to upload it to Ogle servers. Ogle servers will do something with the image. First, it's going to store it to a database so it can be used later. And then it's going to find similar pictures, right? It's going to find all of these memes and then send them back and make the Ogle user super happy. So under the covers, of course, it's not all going to happen in sequence. It's going to be naturally a multi-threaded, highly concurrent, super performant C++ app because, of course, Luke loves C++. Wants everything to go quickly. So here is a high-level diagram of the software architecture in pictures. When a request comes in, it's going to get split off into multiple threads. In one thread, it's going to do some image compression. It's not necessarily required that it save everything in the image. It could be coming in as RAW. We want to save it as JPEG. It writes it to a 3.5-inch floppy disk, as one does. And then it goes and it does the kind of, let's call it AI part. It does feature extraction. So it extracts some features from the image so that it can then do some retrieval and find those similar pictures. And then it mails them back to the Ogle client via paper airplane. All right. So then, of course, once those two threads have done their work, they join up, and the server action is complete. Now, I've simplified a lot in this diagram. Obviously, there could be a lot more threads and a lot more stuff happening. So I'm just showing the one thread. Of course, in these threads, it's also the case that there's going to be synchronization to prevent things from being overwritten or corrupted. So you're going to have locks. Locks are going to change this order and so on. And this will become important later. But at a high level, this is the idea. And every client is more or less independent in executing this code. So great. So Luke goes and posts this to the App Store. And immediately, millions of users start downloading Ogle. And Luke is sure that he's on his way to be the next fortune in Silicon Valley. He's the unicorn. But then under load, what starts to happen is that Ogle gets too slow. So stuff is loading and it's kind of stuck. And so now Luke has a problem, right? Luke was just poised to become super successful and a mogul, if you will, an Ogle mogul. And now his app is performing really poorly. And this is going to scare away all the users, and he's going to be a failure, and he's going to end up having to move to some other land that is not as exciting as Silicon Valley. Back to Tatooine. All right, so before we talk about how we're going to rescue Luke from this terrible situation, let me talk about another Luke. This is cool Luke. This is Luke in the 80s. So the sunglasses, the Ray-Bans are meant to show he's in the 80s. Of course, in the 80s, those of you who are old enough to remember know there were no cell phones. And when people had computers, they didn't look like this. They looked like this. Image resolution also was kind of lacking. So your cat might look like this. So fine. So this is Ogle in the 80s. And of course, being an Ogle application, being an application in the 80s, it has to have a really 80s name. So here's Ogle 84 1.0. And so, this is what Ogle does in the 80s. It has a text interface. It goes and searches the database and it comes up with some results. All right, great. Now, the thing is that Luke in the 80s and Luke in the present day, whoops, I went a little too fast. Luke in the 80s and Luke in the present day both have this problem that things are slow, right? So what happened? So in the 80s, of course, computers were really slow, and but they got faster and faster over time. So notice these two graphs. So the graph on the left is transistors in millions. The graph on the right is clock speed in megahertz. And it's important to note that these are log scale graphs. So these X's are actual points of processors in terms of the number of transistors and their clock speed over time till roughly 2003. And what you can see is that these lines look almost the same, right? So as the number of transistors got small, basically transistors got smaller and smaller, so you could pack many, many more of them onto a chip. We were able to actually increase the clock speed of these processors faster and faster, and the two kind of kept equal pace, and this was great. So what this meant was, literally, you could just buy new hardware every year or every 1.5 years, and your code would automatically run a lot faster. So that was a great situation. Again, I feel bad for those of you in the audience who are too young to remember this. What would happen is you'd buy a computer, and then your next computer would blow that other computer out of the water. And this happened over and over and over again. And we just got used to it, and we thought it was going to last forever. So in the 80s, which you can see is really early in this curve, right? It's like in the middle of this. Everybody expects this is going to go on forever. And those of us in the future know that it doesn't. Performance improvement in the 80s, it was hard to get performance out unless you were just willing to wait. So if you kick back and wait a year, your code will magically run almost twice as fast. And so honestly, Luke's best option in the 80s, cool Luke, was to just go find a beach, get a mojito, and chill. And then 1 year later, come back and be like, well, everything is now twice as fast. Problem solved. So those were great times. Many mojitos were consumed. They are delicious. It is a wonderful time to be a performance engineer. However, in the present day, that is not the case. One sad tear. The problem is that performance is no longer so easy. No more mojitos. So here on these two graphs, I've illustrated what would have happened if the trends had continued as expected. All right, so it's pretty straightforward, straight line interpolation. Unfortunately, while transistors followed this trend, they continue to follow this trend. In fact, transistor counts continue to increase. This is, in fact, what is known as Moore's law. Moore's law is not yet dead. The rumors of its death have been exaggerated for quite some time. Eventually, it's going to run out of steam, but it has not yet run out of steam. However, there's another phenomenon, which is the phenomenon on the right, which turns out to be actually separate from Moore's law. It's a phenomenon called Dennard scaling. And Dennard scaling is what allowed these clock speeds to keep getting ramped up as feature size diminished. Unfortunately, it has now become dominated by power and current leakage on these chips as the feature sizes have gotten smaller. And in short, the chips are just too hot to be able to actually pump them up to a higher clock speed. So while we might have hoped we'd be in a land of 100 gigahertz processors, if this trend had continued, we are not, right? We're in the land of 3 gigahertz processors, 4 if they're overclocked. So this means that really performance is kind of stuck. We do have more transistors. This means that we have to work a lot harder if we want to get performance. How do we exploit those other transistors? They're in the form of multi-core. They're in the form of GPUs. They're in the form of accelerators. This is all a lot more work than sitting back and drinking mojitos. So unfortunately, it is hard to harness all of these additional processor features. And the result has been that performance matters now more than it ever did. So this crowd obviously appreciates performance, but I did a roundup just looking at iPhone updates. And iPhone, under the covers is running basically C or C++, whether it's objectionable C or not. And at the end of the day, many of these applications come up and say bug fixes and performance improvements. Bug fixes and performance improvements. My favorite message was from Yelp. We've decided to start referring to performance improvements as app engine calibrations because it sounds cooler. Therefore, for this version, we've further calibrated the app engine. Okay, fine. But every single application basically is getting shipped, and then it runs into performance problems. So every app needs to improve its performance, more or less, or calibrate its app engine, depending on your preference of terms. So why is this so hard, right? I mean, it's hard to get programs to run correctly, but when they fail because they ran incorrectly, you can tell. You're like, oh, you do some sort of root cause analysis, and you're like, oh, this shouldn't have printed out foo when it was supposed to print out hello world. Performance is much more complicated. Like, it runs slow. Why is it running slow? So it turns out that there are actually two big problems with how performance is being analyzed and how we use performance profilers to actually get at how to make programs run faster. So in the rest of this talk, I'm going to talk about the right way to do performance analysis. I'm going to talk about some pitfalls that you might not be aware of that have arisen because of the complexity of modern day hardware. And then I'm going to talk about performance profilers, why existing performance profilers fall short in this modern brave new world, and how to do it better. So first, I'm going to focus on, like I said, performance analysis, how to do it right. And I'm going to walk through the typical way that performance analysis works. So here's Luke. Luke's got program A, and here's some code. It doesn't matter what the code does, but Luke has an idea. Luke says, I have an idea of how to make this run faster. So Luke goes and, refactors some code, rewrites some things, reorders some things, factors out some fast paths and so on, right? And eventually is left with a new program. And this new program is A prime, all right? And so Luke now wants to know, well, was he successful, right? So he had this great idea and said, I made a bunch of changes. And now how do I know if it's faster? Well, the way he's going to know that it's faster is he's going to test it, right? So he has some input program or input data, and he runs it. He runs it on A, which is the old version, and it took 90 seconds. Great. He runs it on A prime. It takes 87.5 seconds. All right. So that is 2.8% faster. This is clear proof that Luke is a genius, and 2.8% faster. Huge win, right? He's a gigantic genius, and he's radically improved the performance of this code. All right. So fine. He's done, right? So some of you may be aware that this is not really how things work, right? You run things, you run it one time, you see an improvement. You might be thinking, well, yeah, it's faster this one time, but what about variance, right? Computers have a little bit of stuff going on. They have maybe background demons that wake up. Maybe there's other things about the load that are going on that you want to be careful about. So you say, well, I'll run it more times. So let's go crazy. We're going to run it 30 times. All right. So we run A prime 30 times, A 30 times. And you can see on this graph that it's pretty clearly a separation between the old version A, which is in blue on the right, and the new version A prime, which is in green on the left. And in fact, it's still on average 2.8% faster. Great. Luke is a genius. I ran it 30 times. Luke ran it 30 times. It's 2.8% faster. Done. Print. Ship. But not so fast. So why is A prime faster than A? You might think that the reason is, of course, the code change. That Luke is a genius programmer and figured out to change the code like this optimization. But it turns out it could have been just an accident, basically a coincidence. So this is somewhat surprising and distressing. You can see Luke looks very sad by this prospect. let me dig in a little bit and explain what I mean and why this can happen, and why small percentage increases in performance, and even pretty substantial ones, can actually be a total accident, and why you have to be really, really careful when you're analyzing performance. So there's a beautiful paper by Todd Mitkowicz and colleagues. I'll show you the actual paper title in a second because it's also brilliant. And what it shows is there's a huge impact of layout, that is where code and where data ends up in memory, on performance. All right, so let me go to the next slide. So this is the title of the paper, Producing Wrong Data Without Doing Anything Obviously Wrong. You can look this up online. It appeared at the ASMOS conference in 2009. And what it shows is there's a bunch of things that seem very minor and seem like they shouldn't have any impact on anything, and yet they can have really, really large impacts. So what are some of those things? So one is, suppose your makefile changes. When your makefile changes and you change where the .o's are, so suppose you literally had foo.o and bar.o, and you reorder them, and you make it bar.o and foo.o. You've now changed all the function addresses. This can have a huge impact. Here's a quite surprising one. Environment variables. You might think environment variables clearly should have nothing to do with performance, but it turns out in most operating systems, the environment variables are actually loaded into memory, and then the stack is loaded afterwards. And what this means is that the size of the environment variables has an effect on where all of your stack frames end up in memory. Okay, so it's like, yes, this changes addresses. How much of a difference can it make? Well, it turns out pretty huge. In fact, it can be larger than the impact of -03 versus -00. That is to say, highly optimized code versus just compile the most brain-dead way possible. So you can get swings of 40% just by changing these apparently innocuous things. And so, yes, Luke didn't change the link order, and maybe he didn't change the environment variables, but what did he do? Well, what he did do is he changed the code. And when you change the code, you are changing the addresses of all of the code, right? So if you move this thing here, you've shifted everything else down. So you've moved a lot of things around. So it could have been the case that here, some hot code ended up mapping to the same cache set. So the way caches work, if they're not fully associative, is that they are split into these things called sets. And there's a limit of how many entries can end up in the same set. And so if you have too many things that map to the same set, you get misses that aren't because your cache was full. It's just because they all map to the same set. And so it's getting poorly utilized. This is referred to as a conflict miss. So that could have been the case in A, and then by total accident, by just blind luck, A prime ended up moving things around so that stuff and the top thing no longer maps to anything that conflicts with it. See, there's no conflict. And so now you get a performance increase because you're taking better advantage of the cache. So there, in modern architectures, there are instruction caches and data caches. At the lower levels, they're usually together. At the higher levels, they are not. That is closer to the CPU itself. You have a separate instruction cache and a data cache. So moving around instructions can have a big impact. Moving around data can have a big impact. So obviously the culprit here is the cache, and we should all get rid of caches. That's not true. We definitely don't want to get rid of caches. They have a huge impact on performance. But it turns out, sadly, the cache is not the only thing to blame here. Modern chips are super complicated, and they have lots of performance-sensitive microarchitectural features that depend on some sort of function of the program or data addresses. So this is not a complete list, but there's the cache, there's the branch predictor, which tries to decide, well, where am I jumping in my code? And it has tables, and those tables are based on the program counters, which are connected to the addresses of code. And if they fill up, then you can end up with branch predictor misses caused by conflicts. It can be a problem in the TLB. The TLB is the thing that maps virtual memory to physical memory. The TLB is also fixed size, and it also can use, affected by layout, usually not because of hashing, but because of capacity. And if stuff suddenly is spanning 2 pages when it used to be on 1 page, you can actually create TLB pressure, and that can have a very large impact on performance, because when you miss in the TLB, you have to go out to main memory, which is quite far away. So it's many, many more cycles. Beyond that, there's the branch target predictor, which tries to predict where a jump is actually going to go. Modern chips also have very sophisticated prefetchers, which try to anticipate where your memory is going to be loaded next, so that it can hide the latency of bringing it in from RAM. Again, all of these things depend on addresses. So in a way, it's blaming any layout. The layout is a problem. So fine. So you might be like, okay, fine, Emery. Yes, there's all this complexity, but I don't care. A prime freaking rocks. A prime is 2.8% faster, or whatever I said. All right. And you're like, good, print 2.8% faster. Fine. Okay. So I agree with you that it's true, maybe that it's faster, and maybe it was just blind luck, but it is faster. So great, let's keep it. But here's the thing. So yeah, it's faster today, but any other change you make can upset this behavior, right? And you can end up right back where you were or worse. One more call to new is going to change the layout of your entire heap. If you change one class and you add a method or you move some stuff around, you're going to disrupt the layout, right? Obviously, if you change even some lines of code, again, it could basically throw everything away. There's some things that are really more insidious. If you upgrade a library, that library is changing layout, right? And this happens all the time. Here's the craziest part. This has personally burned me. This actually happened to me with a student where my code, where my suggested optimization ran faster on my computer, or apparently, than on his. But it turns out that running in a new directory changes layout, right? So if you are in /user/Vader, you change to user/Luke, you're off by one character. Now you've changed the environment variable size, right, by one character, and that can actually shift things enough to have a significant performance impact. And in fact, what happened in particular with me and my student was that we have different usernames, and they have different lengths. And the username gets copied into the environment variable, and then that changed layout, right? So obviously we should all just do this and all be like Luke all the time. But you may not want to tell all of your users that they should be changing their usernames, all right? So again, not only is this the case for performance, like I'm just trying to optimize code, but all of these caveats apply to performance regression, right? The exact same thing can happen. I made some changes in the code, performance drops, and I'm like, oh my God, back out that code, right? But it might be tomorrow when I put in a little more code, all the performance will come back because all I did was shift around some layout. It had nothing to do with me per se. It was just kind of collateral damage. So this is pretty grim. Layout is really brittle. And now we're in this world where it's like, well, I don't know what did anything, right? So layout bias is measurement. Can we eliminate the effective layout? That seems weird, right? Like, how do we lay new things out and then avoid the impact of these things? So what I'm going to talk about for the next chunk of my talk is how we can eliminate the effective layout. And if you eliminate the effective layout, if you incorporate randomization, then randomization actually allows you to see through all of these layout effects, and you can do performance analysis. And so I'm going to talk to you about how we did that. So we built a tool to allow us to do this sort of performance analysis. And then the conclusions are rather bleak about the hope of compiler optimizations taking out of this hole that we're currently in. So we built this system we call stabilizer. Like I said, memory layout affects performance, and it makes performance evaluation difficult. What we're going to do is we're going to use randomization to eliminate the effective layout, and I'll explain how. And I'll show that it enables sound performance evaluation. And by sound, I mean I can actually say this code change was responsible for an optimization regardless of its impact on layout. And so it is really due to that particular thing and not due to collateral damage. All right, and I'm going to do some case studies and talk about those as well. So what does stabilizer do? This is something that part of this you could actually do yourself in your own code pretty straightforwardly. Stabilizer actually depends on LVM. It randomizes the layout of a lot of things. So it randomizes where functions end up getting put. It randomizes stack frame sizes, which affects the offset of where things end up in the stack. It randomizes heap allocations. So it has a randomizing heap that ensures that one allocation here or there is not going to have an effect over time when you do this randomization. So it doesn't just do this once. It doesn't do it at startup. It does it repeatedly as the program is running. So the code is running and it's shifting things around, and then it shifts things around again and shifts them around again. And you might be thinking, my God, that's crazy. Why on earth would you do that? So the reason is that if the layout is constantly shifting and you test one thing with it shifting and another thing with it shifting, and they're random, and you see an effect, then the only cause could have been your change, because you've randomized out everything else as a cause, right? It's the exact same insight as randomized control trials for drug testing, right? You randomize who's in group A, you randomize who's in group B, you give everybody a drug. If the drug has a significant impact, then you say it's the drug. It's not because everybody comes from a healthy place over here and from a terrible place over here, for example. All right. So by definition, a completely random layout can't bias results. That's the definition of bias. All right. So we built this tool we call Stabilizer. Let me show you what happens when we run Stabilizer and we go back to this idea of doing performance evaluation. So we've got our A and our A prime. This is Luke's optimized version. And we run it and we get a curve now. Now we get a distribution, and I'll explain in a couple slides why we get this kind of more broad distribution that's kind of a bell curve shape. But take a look at this graph. Now, if I could see you all, I would ask you to raise your hands, but I can't. So I'm going to ask you to, at home, raise your hand, even though I can't see it. Tell me if you think, by raising your hand, which I can't see, if A prime is faster than A, right? So A prime is the green one. The average is centered around 87.5 seconds. The blue one is centered around 90.0 seconds, all right? Now keep your hands up, okay? So think to yourself, yeah, probably most of you agree. A prime pretty much looks faster than A. There's some overlap, but it's faster than A, all right? Now, I'm going to advance through some slides, and keep your hand up if you still believe A prime is faster than A. Now, it's getting closer, right? The overlap is a lot larger. And now, how about here? Is A prime faster than A? So what you all are doing right now, probably, is you got less and less comfortable as these curves got closer and closer together. And what you're applying is something that I like to refer to as eyeball statistics. You're eyeballing these two curves and you're saying, God, that curve, wow, they're far apart. That looks great. They're closer. I'm less happy, right? And then obviously if it swaps, then definitely a problem, all right? That's great. It's totally reasonable to do this. It's not very rigorous or scientific. It turns out that eyeball statistics is not actually a thing. If you go to Wikipedia, you could ask for it to be created. Please don't ask for it to be created. It is a terrible idea. This is not how we do statistics. This is not how you do analysis. So when you have your graphs, right, you have these curves, what you're actually supposed to do is apply some sort of real statistical technique. So there are classically two approaches. I'm going to focus on one. This one is referred to as null hypothesis significance testing. And in null hypothesis significance testing, you assume a null, which is that there's no difference, typically. And then you ask the question, what is the likelihood that I would see this result by random chance? All right? So if the result, the probability is extremely low, like it's 1 in a million that this would happen randomly, I might be very convinced, oh, that's a pretty significant difference. If it's 1/2, like I flip a coin and I would see that kind of result, I would probably not be convinced that it's very important, right? So this is the whole notion of significance testing. So you ask if A prime equals A, what is the probability of observing this kind of gap? It turns out this is easy to compute for the normal distribution. You don't need a normal distribution, but if you can get one, you should take it. It makes analysis really easy. So you all have seen the normal distribution before. Roughly 68% of things are going to be clustered in one standard deviation away from the mean, and so on. And we'll get back to this in a minute. again, like, I just want to stress, you don't need normal distribution to do statistics. It just makes things easier. But we are going to be relying on it in some parts of this talk. So what we're going to do, instead of looking at green and red and saying these seem comfortably far apart or they do not, we're going to actually pose this as a null hypothesis test. So we're going to say, if the probability of it happening by random chance is low enough, then we're going to assert that the speed up is real. And because we're doing randomization, we're going to know that it's not due to the effect on memory layout. All right? It must be due to the actual code change made by Luke, our hero. So I've mentioned that we repeatedly randomize the layout. And you might be wondering why on earth we would do this. And it turns out that one randomization is just simply not enough. So here is some actual data where we ran a program and we did one random layout per run. And you can see that you end up with a very non-normal distribution. Things are totally separate. It basically is like there's a good place that one of the random things when you start random ends up in, and then there's a kind of bad place that most of them end up in. I'm sorry, the other way around. This is the good place where it's faster, and the bad place is where it's slow. However, repeated randomization, you get everything in a curve. This is real data, by the way, and it really does look like a normal distribution for very good reasons. So let me explain why you get this beautiful tight curve around this spot. So what stabilizer does is it generates a new random layout every half second. This is a tunable parameter, but that's what we stick with. And the total execution time is, of course, the sum of all of those periods, right? So you have randomized, run, randomize, run, randomize, run, and you just add them all up. So this is pretty obvious. But it allows us to appeal to the central limit theorem. So we have the sum of a sufficient number, if your program runs long enough, that a half second, say it runs 20 seconds or 100 seconds, this should be sufficient. They're independent because they're randomized. They're identically distributed because they come from the same code. They're random variables because they're random. That's the central limit theorem. So no matter what happens here, whatever the distributions were originally, when you add them up after doing them all random, you're going to get almost certainly, unless something is skewed in some very special way, you're going to get a normal distribution. And so this is actually something that you could do with stabilizer. If you wanted to make sure that your performance was in fact stable, you could use stabilizer and have this randomization, and you would know that the chance of having a performance outlier, no matter what you do, is going to be quite low. But we're not going to use that, we're not going to take advantage of that here. We're going to instead use this as an analytical tool for doing a case study. So we want to understand whether LLVM's optimizations actually matter. So we're going to do it on a suite of benchmarks. We're going to do it one at a time. Then we're going to do it across the entire benchmark suite. So we built these benchmarks with Stabilizer, which again is just an LLVM plugin. You can optionally just randomize the code or just randomize the stack or just randomize the heap. By default, it randomizes everything. We built it so that it had all of the support, and then we ran the benchmarks. So again, we're going to follow the same sort of trick as, we're going to run things 30 times. 30 is too many. But anyway, you run the things a bunch of times. You drop the results into the statistics package of your choice. Let's say it's R. And again, you're going to get a resulting graph. You're not going to ask this question because, again, that's eyeball statistics. What we're going to do is we're going to say, assume the null hypothesis is true. There's no difference. How likely is it that we would observe this by chance? For this, we're going to use the student's t-test. This is the incantation to do this in R. There's lots there's every statistical test under the sun inside of R. We actually have a separate project to make running statistics much, much easier that we call TEA. I'd be happy to talk about that offline. It's a Python package. But that's immaterial. Right now, what we're going to be asking is this probability, which is generally known as the p-value, low enough that we consider it to be unlikely? So I said 1 in a million before. That's very, very, that's super rigorous. Most people, when they do science, pick a p-value that's not quite so stringent. They say if it was random and it came up 1 in 20 times, that would be enough. Or it comes up 1 in 100 times, that would be enough. So here we're going to stick with 1 in 20. We'll be a little generous. So that's a p-value of 5%. So if the p-value is less than or equal to 5%, we're going to reject the null hypothesis. They are not the same. Random chance is not why these two things are different. They're different because Luke is a frickin' genius. All right. And the optimization is real. All right. So here we're actually going to do this for LVM. So nobody's changing any code manually. We're just running LVM -O something versus -O something else. And I can tell you, you'll be unsurprised to learn -O1 versus -O0 makes a big difference. Optimizing versus not optimizing is indeed real. -O2 versus -O1 also makes a significant difference. And I should note, there is a big difference between significance, which is that, yes, it's unlikely that you'd observe this by chance, and the effect, right? So you can see in the middle, for example, well, so on the far end, you can see a it's significant and it's substantial. It's a 20% improvement. That's pretty sweet. Here in the middle, you can see an actually one non-significant difference, but all the ones to the right are significant and they're very, very small. So just because it's unlikely that you observe something due to random chance doesn't mean that it matters. But if it's basically random chance, then it definitely doesn't matter. On here, strangely, we observed some statistically significant performance drops. And this means that they actually were just lucking into layout optimizations. And it had nothing to do really with the optimization itself, because the code optimizations themselves really sort of intuitively should be increasing speed, but actually they may have been overfit to these particular benchmarks. All right, so that's -O2 versus -O1. Great, you should all use -O2. Sounds good. How about -O3? So you can see that these numbers have plummeted. So I actually have to zoom in from going to -10% to 20% to 0% to 1.5%, so we can actually see these results. And you can see it's really quite the mixed bag. You have some things that are significant, quite a few things that are statistically not significant at all, and a few statistically significant, very, very minor performance degradations. All right, great. So what do these results mean? So the thing is that those results that I just talked about are about individual benchmarks. We really want to be able to say something about all of the benchmarks at the same time, right? So we run this benchmark and that benchmark and those benchmarks, blah, blah, blah. We get a bunch of graphs. Some are faster, some are slower. And the question we wanted to ask was, is -O3 faster than -O2? Like, is there a statistically significant difference? Here you can see that -O3 is slower, and then here -O3 is faster. So is -O3 faster? We look at these graphs. This is eyeball statistics. Again, not the way we should be doing things. Let's reframe it in terms of the null hypothesis. The null is that they're equal. And is it likely that we would observe these differences by chance? So the way to do this for more than one thing is a technique called analysis of variance, or ANOVA. This is a sort of hideous incantation in R. Not my favorite language, in case you were doubting. However, this is a way of getting at this particular thing. We model it as the effect of the optimization plus some Gaussian error, and we run this analysis, right? So again, we're going to test if the p-value is less than or equal to 5%, then we're going to reject the null hypothesis. Great. So we run ANOVA with -O3 and -O2, and the p-value that we get is, drumroll please, 26.4%. Our threshold that we set was 5%, and it came up that 1/4 of the time you will get this impact that you observe just by random chance. In effect, 1 in 4 experiments will show an effect that kind of doesn't exist at all. It's just a kind of coin flip. So obviously we fail to reject the null hypothesis. And in essence, we have to conclude that the effect of -O3 over -O2 is indistinguishable from noise. So that's too bad. It means that Luke is stuck. One kind of funny thing about -O is that you actually will see projects checked into GitHub that have -O9. And I think this is beautiful. and sweet. This is people who are just so optimistic about the ability of optimizers to do something. Unfortunately, -09 is just -03. All right, great. So what should Luke be doing, right? Luke can't use a compiler to get him out of this. He's going to have to use a profiler. So to a first approximation, what do profilers do? So profilers, this is a bit of a caricature, essentially look at the functions that ran. They give you the number of calls to each function. They give you the runtime for each function. There are different profilers that can be more precise. They can do things at the levels of lines. There's other somewhat more sophisticated profilers. But at the end of the day, the guidance that you get from a traditional profiler is, here is some frequently executed code and code that executes for a long time. Those are the things that a profiler is going to surface for you. And so you might think, well, that's probably where Luke should focus on his performance, right? Those are the things that matter. So would this speed up Ogle? So basically, Luke goes and runs a profiler and finds the code that is frequently executed and runs for a long period of time, applies all the optimizations that he can think of to that code, and then runs it. And it turns out it made the loading thing blink faster, but it didn't do anything else, right? This is really sad. So why did that happen? Well, frequently executed code and code that runs for a long time, that loading dialog, right, that message shows up the whole time that the thing is happening, and it's executed all the time. So in short, profilers just do a bad job finding important code in parallel, asynchronous, and concurrent programs. So we need to do better. We need some way to help poor Luke. So ideally, what we would have is something that we refer to as a causal profile. So a causal profile answers this question. So the graph that you see, the x-axis is speed up, to the right is better, and that's speeding up like a particular line or function. And then the y-axis is overall program speed up. And so you can see, like here, if I speed up this red one by this much, just that component, then I get this overall speed up in the program. That means your program will run this much faster. So if we had a graph like this that was handed down to us on a tablet from Mount Sinai, we would just look at it and we'd be like, oh, I will probably start optimizing the yellow thing first. Then I'll try to optimize the red thing, and I will never spend any time on the blue thing. Right? So this is perfect. This is essentially God or an oracle telling you, here's what you should be doing. Now, of course, this is great, right? It would be wonderful to have this information, but how are we going to get it, right? We need to know this change has this effect. So what we're going to do, and I'll explain how we're going to do this, is we're going to run experiments. And so the experiments that we're going to run, we call performance experiments. Now, if we could magically speed up a component, like here, this is the indexing search. If we could speed it up magically, we could observe, oh, if I speed this up by this much, and I look at the end, you can see that that's the effect on the whole program. So that would be awesome, right? And then I could do it again, right? So I'm getting more and more points for this graph, right? I speed it up a little more. I observe that there's more speed up and so on. And then I do this for every single component in the program, right? I discover no program speed up by, accelerating, saving to the floppy disk. Unfortunately, that's magic, right? You can't just speed up code arbitrarily. If you could speed up code arbitrarily, you wouldn't be speeding it up a little bit and observing its effect. You just do this, right? You would speed up everything to take zero runtime. So fine. So we're clearly not going to do this, and we can't do it. It's impossible because sadly, magic does not exist. I'm sorry to break it to you. So what we're going to do is we have this clever trick, which is essentially based on the theory of relativity. What we're going to do is we're going to speed up a component by slowing everything else down that's running concurrently with it. So we'll have the relative effect of having run faster. So here, what we're going to do is when the transmission part is running, we're going to slow down the saving part. And then you'll observe that this speed up, which is really slowing down everything else, has this impact. And so then we can add a point to this graph that corresponds to this, right? So we just are going to rinse and repeat doing this. We're going to run the program, apply these speed ups, which are really slowdowns. So they're virtual speed ups. and then we're going to observe the impact, and then we're going to get these graphs. And we can do this for every single component. Again, something is running, you slow down the stuff, the thing that you're testing, you slow down everything else that's running. We do this with sampling and other techniques that we describe in detail in the paper that I'm happy to point you to. And you observe all the impacts, you get graphs, eventually you get all the graphs for all of the components. Now, I just want to draw your attention briefly. Obviously, you can see there's some that are increasing, there's some that are flat, and there's some that are actually below the line, where if you had been told you should work on optimizing that code, you would have slowed down the program. And you might be thinking, how the hell could I slow down the program by speeding something up? But aha, in the world of concurrency, you can have problems where you have too many things that show up to a lock at the same time. You have lock contention. And this causes some significant performance degradation. You can have a terrible phenomenon called false sharing, where things are banging on the same cache line. If you accelerate one that's banging on the cache line more, you're hurting the other one. All right. So there's lots of complexity in this. And the nice thing is that a causal profile would reveal this to you, so you wouldn't waste your time trying to optimize things that would have a bad effect on your overall program. All right. So let's see what happens if we apply causal profiling to Ogle. So here's Ogle. Right. This is the whole thing I showed you before. So let's implement Ogle. If we're going to implement it, we're going to have to answer a couple of questions, right, about performance. So first, we care about latency, right? How long does it take between a request and a response? That clearly matters, right? How fast do results come back is another question, right? How many results are coming back in total? That's what we call throughput, right? So there's two different things that we want to actually test or optimize for. And it turns out that existing profilers only handle the latter. They only really deal with throughput in a very oblique way. They really are just like, I ran my program and it spent a lot of time doing something. It's not really connected to latency or throughput. But as you'll see, causal profiling is directly related to these things and lets you answer these questions precisely. So the way causal profiling works departs a bit from traditional profilers, and it requires a little more assistance for the programmer. So suppose Luke wants to send responses faster. That is to say, there should be more responses coming out per second. So that's a throughput question. So what you do in a causal profiler is you mark this as a so-called progress point. And every time the code runs, it goes and it increments a counter, right? And so you want that thing to happen faster and faster. So when you have many of them in flight, right, many requests coming from multiple users, right, it's getting bing, 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 bing on all of them. And one progress point is going to measure throughput. And then it's going to test the effect of these experiments on throughput. All right. So that's one progress point. If I speed up something, how much faster do I get output on this progress point? So great. So that's throughput. What about latency? So suppose Luke wants to minimize response time. So here we have another notion of progress points that we call latency progress points, which are just a begin progress point and an end progress point. So you place in your code a begin, you place like the start of a transaction and at the end of the transaction, and then the causal profiler is going to actually optimize to reduce latency. The way it works is that every time something comes in, it actually updates the number of transactions in flight. And when it leaves, it drops the number of transactions in flight. It doesn't need any more plumbing in the code because we take advantage of this lovely result from queuing theory called Little's Law. Briefly, this is a restatement of Little's Law, but latency essentially on average equals the number of transactions in a system divided by the throughput. And we already know how to measure throughput, which is through this measure of how many things run through the either one of the transaction points, and then we have the counter. And that's enough to allow us to optimize for latency. So we built a causal profiler for Linux. It ships with Debian and Ubuntu. It's also on GitHub. Unfortunately, it does not work on Windows, but what are you going to do? What you're going to do is you're going to use Linux to do this. So this is how you run it. You say cause run dash dash dash. That consumes all the command line arguments. Then you write your program code. So just as usual. And the important thing to understand here with cause is that it actually goes back to the beginning of the talk. These performance experiments are random, and this randomness disrupts the way things are actually scheduled. So when an experiment happens, it randomly picks some line of code that's running and runs the performance experiment either for latency or for throughput. And because things are concurrent and because things are asynchronous and because they're being probed in random ways, you get the effect of it being random. And so this means that the results are going to be due to the performance change that is predicted. So let's go ahead and use it with Ogle. So if you are running Ogle, right? Well, we need code to run Ogle. So we took a bunch of programs from this thing called Parsec, and we combined them. So we have a thing that does deduplication. So when you take an image, it compresses it, and I'll explain how. We have a thing that does image comparison called Ferret. These all come from Parsec. And then the database, we use SQLite. So let me focus on Ferret, which was quite easy and quite nice. So this is a resulting causal profile produced by cause. And so it's at a line level, and you can read this exactly as I showed in the graph before. That was a little bit prettier and more abstract. It goes from 0 to 100 on the x-axis. That's how much you speed up a line. And then the y-axis is overall program speed up. So we were just testing throughput here. And the cool part is that these lines of code corresponded to discrete parts of Ferret, to a ranking part, an indexing part, and a segmentation part. And the way that Ferret was structured is that it actually sets up a number of threads. So it comes up, it says how many CPUs you have, it figures out how many threads to create, and it evenly spread them across. So as you can see, the gray part, feature extraction, right? This is this image pipeline. The feature extraction part was not highlighted by cause as being important at all. So it probably needs fewer threads. So what we did is we just took away some of its threads and gave them to the ones where we expected there to be more bang for the buck, as predicted by cause. And the result was a 21% speed up. So great. So that was great. We're all happy with a 21% speed up. Because it's random, we have high confidence that's going to be a robust result. So it's not just here today. What did it predict? Well, cause predicted that if you basically increase the ranking throughput by 27%, which is what we did. We increased from 16 to 22 threads. If you go and you look at the graph, that's 27% on the x-axis. And on the y-axis, you get this result, which is a 21% improvement, which is exactly what we observed. So cause is actually doing, not only pointing us to where the optimization makes a big difference, but it's doing it accurately. And this happens over and over again. So we did this with these other applications like dedupe. So in dedupe, the way dedupe works, it's compression via deduplication, like its name suggests. So if you have your image here and somebody else has already saved this meme, you can see that there's a pretty common chunk, right? This is it. And so rather than representing every image as an individual item, you represent it as multiple items. So here, we've split up an image. So Grumpy Cat 1 is now these three pieces, the top, the bottom, and the middle. And funisawful.jpg is now the three pieces, and one of them is the same big giant chunk in the middle. All right? So the way dedupe works, it applies a hash function, and that it maintains a bunch of buckets for where all of these things are kept, right? So it computes a hash function over an image, and it jams it into the bucket. It's a pretty straightforward linear chaining hash table. And so it does the usual stuff. It adds everything to these buckets. Great. The hash table is accessed concurrently by many threads. Cause actually said, hey, this is a bottleneck. And we were like, oh, maybe there's something really stupid about this hash table. Like it's got one big lock. It does not. It has many locks. So we were like, that's confusing. So it's not a concurrency problem. What on earth could it be? So cause specifically said that code that was in this list was important, that the loop was like where it iterates through this thing looking for a hit or looking for a bucket, an empty place to insert something was very important. So we thought, wow, maybe the hash table is just too small, right? There's just too many of these, like there's maybe a small number of these things. And we said, okay, we need to spread out the list better. And so we added a bunch of hash buckets. And so in principle, more hash buckets should lead to fewer collisions. But in practice, we got no performance improvement. So what else could be causing collisions? And somebody at home has definitely got the answer here. The answer is the frickin' hash function. So the moral of the story here, a brief moral, is don't try this at home. Don't build your own hash function unless you know what you're doing. Here, we actually graphed the utilization of the hash function. So we created 1,024 buckets, and then we counted how many things ended up in each bucket. And you can see the utilization is a catastrophe. It's 2.3%. Most of the buckets are empty, and a bunch of them have like 100. And it turns out the reason is that, in effect, there was a normal distribution because it just added values taken from these images. And the images are effectively random. And so you get the central limit theorem, and you get a normal distribution. But you do not want a normal distribution for your hash function. You want a uniform distribution for your hash function that spread things evenly. So my student actually changed in probably the greatest optimization per effort ever, changed one character in the hash function from a plus to XOR, and it became 82% utilization. So it's not a huge speed up. This led to a 9% overall speed up, which is not nothing, but it's definitely a big bang for one character of change. And so it turns out we can actually see what cause predicted and how closely its prediction queued to the result. So the blocks per bucket determines the number of iterations to go through this list, obviously. And on average before, it was 76.7. Afterwards, it was 2.09. So that's a big improvement, right? So an average of 2 instead of 76. This is a 96% traversal speed up. When you look at that graph, which I'm not going to show, this gives you a 9% predicted speed up, which is exactly what we observe. Finally, I'm going to show you something that is really a kind of performance optimization opportunity you would never see any profiler ever deliver. I mean, cause goes beyond previous profilers in that it handles, obviously predicts things, it does throughput, and it does latency profiling, but it also finds things that you would never look for, that would never show up ever. So let me show you an example from SQLite. So here in SQLite are some causal profilers, and you can see that there's some weirdness happening. We speed up some lines of code and things drop. And this usually indicates some sort of a contention problem. So it's either false sharing or a lock. So SQLite, for those of you who don't know, it's a simple SQL database. It's crazy. It compiles to one big C file. It's in everything. It's in your browser. It's on your phone. There's probably 10 instances of SQLite running on every device you own. And it has this super hacky, so the thing is written in C and not C++. And so they rolled their own vtables. So they have this thing where it's defined at compile time. They have this global config if it is thread safe. And it has members where it uses a lock, like it does a real unlock when you do unlock. It does this thread safe get size. It does a bunch of stuff that is thread safe. If it is not compiled with thread safe, then the unlock is a null, right? It's a no-op. The lock is a no-op, and it uses things that don't acquire locks. Seems like a reasonable optimization. Fine. It's a little odd that they would do this dynamically in a vtable, but anyway, be that as it may, that's the way it works. So the way that SQLite unlock works is there's a level of indirection, right? So rather than calling something directly, it indirects through global config, and then it makes this function call. So it's an indirect call. And I think, most people in the audience here would be like, well, indirect calls are not that expensive. And some people in C++ land really hate the idea of using virtual dispatch. I think it's a subject of some contention. It's usually pretty fast. The problem is that pthread mutex unlock is also pretty fast. And this is preceding pthread mutex unlock, right? So every single time this is happening, right, and it happens multiple times, these are all the lines that cause is highlighting. It's actually increasing the critical section on all of this code. And the critical section is not much, but it's enough. It's like doubled. So by doubling these critical section lengths, you actually have a big impact when you increase the number of threads because you get a ton of contention. So in sum, we did something where we stripped out the virtual dispatch from SQLite, sped it up by 25%. You've already seen these other performance improvements. We applied it to a whole bunch of other things. We were able very quickly, this is code we had never seen before, I should add. This is code that in general, it was like a question of spend no more than 20 or 30 minutes trying to optimize these programs. And we were able to quickly basically place progress points, run cause, and get shocking improvements in some cases. My favorite is stream cluster and fluid animate. We got 38% and 68% improvements by removing a custom barrier and using the standard barrier. So this is something that you probably would not have found with a regular profiler. So I think that it's getting near my time. So I'm going to conclude. So I presented sound performance analysis, argued that performance analysis or that performance optimizations have kind of run out of steam. So you really need to be using a different profiler, that existing profilers don't get the job done. You should go and use the cause. You can install it yourself on Linux. And with that, I would be happy to take any questions. Thanks for your attention.